Welcome to today's session. In this video, we'll dive into a fascinating problem from LeetCode, problem number 821, shortest distance to a character. This problem is a great way to practice working with strings and distances. Let's get started. In this problem, we are given a string S and a character C that is guaranteed to appear at least once in the string. Our task is to return an array of integers where each value represents the shortest distance between the corresponding character in S and the character C. For example, if S is LeetCode and C is E, we need to calculate how far each character in the string is from the nearest occurrence of E. The length of the string can be up to 10,000 characters, and every character in S will always be a lowercase English letter. The output array, therefore, must also have the same length as the input string, with each index representing the computed distance for that position. Now, let's take a look at an example. If S is LeetCode and C is E, the output array would be 3, 2, 1, 0, 1, 0, 0, 1, 2, 2, 1, 0. Here's how these values are calculated. For S, 0, which is L, the closest E is at index 3, so the distance is 3. For S, 1, which is O, the closest E is still at index 3, so the distance is 2. This logic continues until we reach S, 3, which is E itself, so the distance is 0. This process is repeated for every character in the string, ensuring that we calculate the shortest distance to the closest occurrence of E at each step. The result is an array where each value reflects the minimum distance for its corresponding index. Let's consider another example. If S is AB and C is B, the output array would be 3, 2, 1, 0. For S, 0, the character is A, and the closest B is at index 3, giving us a distance of 3. Similarly, for S, 1, and S, 2, which are also A, the distances to the closest B are 2 and 1 respectively. Finally, for S, 3, the character is B, so the distance is 0 because B is already at this position. The result is an array of distances that accurately represents the shortest path to the nearest B for each character in the string. Now let's consider the constraints. The string's length can be as large as 10,000, it only includes lowercase letters, and the character C will always appear at least once. This ensures that we don't encounter invalid input, and our task remains focused on finding these shortest distances efficiently. Finally, let's discuss some edge cases. First, if all the characters in the string are the same as C, such as S equals E and C equals E, then all distances are 0 because every character is already E. The output in this case would simply be 0, 0, 0, 0. Another edge case occurs when C appears at the beginning or end of the string. For example, if S equals ABCA and C equals A, the shortest distances are calculated in both directions, resulting in 0, 1, 2, 0. Lastly, for performance testing, imagine a very large input where S consists of 10,000 A's and C is also A. In this case, all distances are 0, and the output is 0, 0, 0. These examples highlight the importance of accounting for different scenarios while ensuring that the solution is efficient even for large inputs. To approach this problem, the most intuitive method we might consider is the brute force approach. Here, the idea is to compute the distance for each character in the string S to every occurrence of the target character C. For each character in S, we traverse the string to find all the positions of C, calculate the distances to each, and take the minimum. While this method ensures that every position is accounted for, it's highly inefficient. The outer loop goes through each character in S, and the inner loop checks all occurrences of C, leading to a time complexity of O(n squared). This makes it impractical for large strings with, say, 10,000 characters. Although simple to implement, it involves repetitive computations and is not well suited for scenarios with significant input sizes. Now, to overcome these inefficiencies, we can use an optimized two-pass approach. This method significantly reduces redundant computations by leveraging two linear scans of the string, one from left to right and another from right to left. The key insight here is that we can incrementally track the distance to the nearest occurrence of C during each pass. In the left to right pass, we maintain the index of the most recent C and compute the provisional distance for each character. In the right to left pass, we do the same but update the distance to account for the nearest C on the right. By taking the minimum of these two distances for each character, we ensure the shortest distance is calculated efficiently. With this approach, the time complexity drops to O(n), since we only traverse the string twice, and the space complexity is limited to the output array, making it much more scalable. This optimized approach not only improves performance but also scales well to handle large input sizes. While it is slightly more complex to implement compared to the brute force method, its efficiency makes it the better choice. The ability to calculate distances without revisiting characters repeatedly is a major strength. For this reason, we've chosen the two-pass method as our final strategy. It reduces the time complexity from O(n)² to O(n), a significant improvement. Additionally, the space overhead is minimal, as we only need the result array to store the output. This balance between clarity, efficiency, and scalability makes the two-pass approach ideal for solving this problem, especially in competitive programming or real-world applications with large datasets. The key realization that makes the two-pass approach so effective is understanding that distances to the nearest C on both sides can be computed independently and consolidated efficiently. This eliminates the need to recalculate distances repeatedly, as is the case with the brute force method. When compared, the optimized approach is more than an order of magnitude faster for large inputs, making it far more practical. While the brute force method might be simpler to implement, it becomes infeasible for larger strings. A single-pass alternative might theoretically exist but would require maintaining complex state for both left and right distances simultaneously, which complicates implementation without offering a significant performance gain. The two-pass method, therefore, strikes the right balance, combining clarity with efficiency, and is the best choice for this problem. To solve this problem, we start with a brute force approach. Given a string S and a target character C, our goal is to calculate, for each character in S, the shortest distance to the nearest occurrence of C. First, we initialize an empty list called distances to store the results and determine the length of the string, n. Next, we use an outer loop to iterate through each character in the string. For each character at position I, we initialize a variable min_distance to infinity, representing the shortest distance that we'll calculate. Inside this outer loop, we have an inner loop that checks every index j in the string. If the character at S, j, matches the target C, we calculate the absolute distance between I and j. The min_distance variable is then updated to the smaller of its current value or this newly calculated distance. After completing the inner loop for a given character, we append the final min_distance to the distances list. Once all characters are processed, the function returns this list of distances as the result. The brute force approach, while straightforward, is not optimal. It involves two nested loops. The outer loop processes each character in the string, while the inner loop checks the distance to every occurrence of C. This results in a time complexity of O(n)², where n is the length of the string. To better understand the problem, note the symmetry in distances. For example, if C appears at indices 2 and 8, the distances to characters around index 2 mirror each other. This symmetry suggests that redundant calculations are being performed in the brute force approach. Additionally, the current method does not take advantage of previously computed distances, which could be reused to improve efficiency. For data structures, we rely on the input string S and the target character C. The resulting distances are stored in a list because it allows easy indexing and maintains the required order of results. The use of a list ensures that we can directly append values as we compute them. The core operations of the brute force method involve traversing the string with two nested loops. The outer loop ensures each character in S is examined, while the inner loop evaluates the distance to every occurrence of C to find the shortest one. The absolute distance calculation, using abs, ij, guarantees accuracy in determining how far a character is from C. The min operation ensures we always store the smallest distance for each character. However, it's important to consider edge cases. If C does not appear in the string, the brute force approach fails, as no valid distance can be computed. This edge case needs to be handled by validating the input beforehand. On the other hand, if every character in S is C, the result is a list of zeros since the distance to C is 0 for all indices. Lastly, for an empty string, the function should return an empty list, as there are no characters to evaluate. To optimize this algorithm, we can avoid redundant calculations by pre-processing the indices of all occurrences of C. Once we know where C is located, we can compute distances more efficiently using a two-pass approach. First, we perform a left-to-right pass through the string, keeping track of the nearest C seen so far. During this pass, we update the distance for each character based on this nearest occurrence. Then, we perform a right-to-left pass to ensure that distances are minimized in both directions. By combining these two passes, we can compute the shortest distance for each character in linear time, reducing the time complexity to O(n). This optimization significantly improves efficiency, especially for longer strings. The final step is to return the computed distances list, which now contains the shortest distances for every character in the string to the nearest occurrence of C. The solution efficiently calculates the shortest distance to a given character in a string using two linear passes. The first pass scans the string from left to right and tracks the most recent occurrence of the target character. For each index, it calculates the distance to this occurrence and stores it in an array. The second pass scans the string from right to left, repeating the process. This ensures that for each index, the stored distance is the smallest possible, as it considers the closest occurrences of the target character from both directions. The time complexity is O(n), where n is the length of the string, making it optimal for this problem. Here, we begin by importing the necessary packages and defining our solution class. The goal is to calculate the shortest distance from each character in the string S to the target character C. First, we determine the length of the string and initialize an array called distances to store the results. This array is pre-filled with the maximum possible integer value to ensure we can later compute the minimum distances correctly. Next, we perform the first pass through the string, moving from left to right. We keep track of the most recent index where the target character C was encountered using a variable called prevCindex, which is initially set to a very large negative value to handle cases where C hasn't been encountered yet. As we iterate through the string, whenever we find the target character, we update prevCindex to the current index. For every character, we calculate its distance from prevCindex and store it in the distances array. This ensures that the array reflects the shortest distance to C when looking only at characters to the left or at the current position. Now, after the first pass is complete, we move on to the second pass, where we iterate through the string from right to left. This is necessary to account for shorter distances to C that might exist on the right side of each character. We reset prevCindex to a very large positive value to represent a scenario where C hasn't yet been encountered from this direction. As we iterate backward through the string, if we encounter the target character, we update prevCindex accordingly. For each character, we then calculate the distance to prevCindex and take the minimum of this value and the value already stored in the distances array. This ensures that each position in the array reflects the smallest possible distance to C from either direction. Finally, once both passes are complete, the distances array is returned, containing the shortest distances for all characters in the string. To solve this problem, we start with an example where the input string is LeetCode and the target character is E. First, we initialize some variables. The length of the string, n, is 12. Then, we create an array called distances filled with infinity, which will eventually store the shortest distances to the target character for each index. Finally, we initialize prev_c_index to -infinity, which will help us keep track of the last seen index of the target character as we iterate through the string. Next, we perform the first pass from left to right. At index 0, the character is L, which is not the target character E, so the distance at this index remains infinity. Similarly, for indices 1 and 2, the characters are O and V, neither of which match E, so their distances also remain infinity. At index 3, the character is E, which matches our target. Here, we update prev_c_index to 3 and set the distance at index 3 to 0 because the distance to itself is 0. From this point onward, for each subsequent index, we calculate the distance as the difference between the current index and prev_c_index. For example, at index 4, the distance is 4 minus 3, which equals 1. Similarly, we update distances for the rest of the indices through index 11. After completing this first pass, the distances array looks like this: INF, 0, 1, 2, 3, 4, 0, 1, 2, 3. Now we perform the second pass, this time iterating from right to left. we reset preb_c_index to positive infinity to start fresh. At index 11, the character is e, which matches our target. Here, we update preb_c_index to 11 and recalculate the distance at index 11. Since the distance was already 3 from the first pass, we take the minimum of 3 in the new distance, which is 11 minus 11, or 0. This updates distances 11 to 0. Moving backward, we update the distances for each index by comparing the existing value in the distances array with the distance relative to the new preb_c_index. For example, at index 10, the minimum of the existing value, which is 2, and the new calculated distance, which is 11 minus 10, or 1, gives us 1. Similarly, we update all the preceding distances up to index 0. By the end of this second pass, the distances array is finalized as 3, 2, 1, 0, 1, 2, 3, 4, 0, 1, 2, 0. This represents the shortest distance to the target character e for each index in the string. Finally, we return this array as the output. Let's go through another example where the input string is aba and the target character is b. The length of the string, n, is 5, and we initialize the distances array to inf, 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 inf. We also set preb_c_index to negative infinity. In the first pass, we iterate from left to right. At indices 0 and 1, the characters are a, which do not match the target b, so the distances remain infinity. At index 2, the character is b, which matches the target. Here, we update preb_c_index to 2 and set the distance at index 2 to 0. For the remaining indices, we calculate the distances relative to preb_c_index. For example, at index 3, the distance is 3 minus 2, which equals 1, and at index 4, the distance is 4 minus 2, which equals 2. After this pass, the distances array is inf, 0, 1, 2. Next, we reset preb_c_index to positive infinity and perform the second pass from right to left. Here, we update distances by taking the minimum between the existing value and the new calculated distance relative to preb_c_index. For instance, at index 1, the minimum of infinity in 2 minus 1, or 1, gives us 1. Similarly, at index 0, the minimum of infinity in 2 minus 0, or 2, gives us 2. After completing this pass, the final distances array is 2, 1, 0, 1, 2, which we return as the output. Finally, consider the example where the input string is ABC and the target character is a. The length of the string is 3, and we initialize the distances array to inf, 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 and set preb_c_index to negative infinity. During the first pass, we iterate from left to right. At index 0, the character is a, which matches the target. We update preb_c_index to 0 and set the distance at index 0 to 0. For the subsequent indices, we calculate distances relative to preb_c_index. At index 1, the distance is 1 minus 0, or 1, and at index 2, the distance is 2 minus 0, or 2. After this pass, the distances array is 0, 1, 2. For the second pass, we reset preb_c_index to positive infinity and iterate from right to left. Since the preb_c_index at 0 already minimizes all distances, no updates occur during this pass. The final distances array remains 0, 1, 2, which we return as the output. This concludes the walkthrough of the solution. Now, let's analyze the time complexity of the solution. The algorithm processes the input string s in 2 passes. First, we initialize a distances array of size n with all elements set to infinity, which takes n time since we are iterating through the array once. Then, in the first pass, we traverse the string from left to right. For each character, we check if it matches the target character c. If it does, we update the corresponding entry in the distances array. These updates occur in constant time for each character, giving the first pass a total complexity of n. In the second pass, we traverse the string from right to left, performing similar checks and updating the distances array by comparing the current and new distances. Again, this pass takes n time. When we combine the 2 passes, the total time complexity becomes n plus n, which simplifies to n. Importantly, this linear time complexity holds across the best, average, and worst cases since the algorithm always performs 2 full passes over the string. Let's now consider the space complexity. The algorithm uses a distances array to store the shortest distances for each character in the string. Since the array has the same length as the input string s, its space usage is O, n. Additionally, the algorithm uses a few variables, such as n, prev_c_index, and I, which require only constant space, or O1. When we add these contributions, the overall space complexity is dominated by the distances array, resulting in O, n. Comparing this with a brute force approach helps to highlight the efficiency of the current solution. In a naive approach, we would calculate the distance for each character by iterating through the entire string to find the nearest occurrence of c. For a string of length n, this would result in O, n, operations per character, leading to a total time complexity of O, n squared. In contrast, the current solution optimizes this process by using 2 linear passes, reducing the time complexity to O, n, while maintaining the same O, n, space usage. Finally, let's provide a mathematical justification for the big O complexity. In the first pass, the loop iterates through the string n times, and each iteration involves constant time operations, such as comparisons and updates, resulting in O, n, O, 1, which simplifies to O, n. The second pass behaves identically, with another n iterations of O, 1, operations, contributing an additional O, n. Adding these together, the total time complexity is O, n, plus O, n, which simplifies to O, n. On the space side, the dominant factor is the distances array, which requires O, n, space. Now, let's address the different cases. In the best case, when all characters in S are equal to C, the algorithm still performs 2 full passes, resulting in O, n, time. In the worst case, when C is rare or even absent, the same 2 passes are made, and the time complexity remains O, n. Similarly, the average case also involves 2 complete scans of the string, so the time complexity does not change. This uniform performance across cases is a key advantage of the algorithm. When solving this problem, there are a few common mistakes to watch out for. First, not accounting for edge cases can cause significant issues. For example, if the target character C doesn't exist in the string, the program might behave unpredictably or even crash. To avoid this, always start by validating that C appears at least once in the string before proceeding. Another frequent issue is using an inefficient brute force implementation. If you calculate the distance for every character in the string by iterating through the entire string repeatedly, it results in O, n squared, time complexity, which can be far too slow for larger inputs. Instead, aim for optimized approaches like the 2-pass or 1-pass solutions, which bring the complexity down to O, n. Finally, be cautious about off-by-1 errors in distance calculations. A common mistake is forgetting to use the absolute value when calculating distances, which can lead to incorrect results. Always ensure you use abs, ij, to correctly compute the difference between indices. Another mistake to avoid is not leveraging symmetry or patterns within the problem. The distances between characters are symmetric around target characters, so failing to recognize this symmetry can lead to redundant calculations. A more efficient approach is to use a directional strategy, calculating distances in one pass from left to right and another from right to left, which minimizes unnecessary work. Additionally, incorrect initialization of distances is another pitfall. Some solutions start by initializing distances with a large arbitrary value, like infinity, without considering the problem's constraints. This can cause confusion or errors. Instead, you should use the maximum possible distance based on the string's length as your initial value, ensuring that your approach aligns with the problem's requirements. This problem is a great test of pattern recognition and optimization skills. It often challenges candidates to identify symmetry or directional properties in the string and use these to streamline their solution. Interviewers typically expect you to understand and explain the 2-pass approach, which involves traversing the string left to right and then right to left for optimal efficiency. It's also important to be prepared to discuss edge cases. For instance, what happens if the string doesn't contain the target character at all, or if every character is the target? How does your solution handle very large strings? Furthermore, clarity is key during interviews. Be ready to clearly articulate the time and space complexity of your solution. The optimal solution should run in O(n) time and use O(1) space, which balances efficiency and simplicity. This problem connects well with other challenges on LeetCode that involve distances and efficient searching. For example, in LeetCode 821, which is the problem we're discussing, the focus is on calculating the shortest distances to a target character within a string. Similarly, LeetCode 34, which involves finding the first and last position of an element in a sorted array, emphasizes efficient searching techniques. LeetCode 849, which is about maximizing the distance to the closest person, shares the theme of distance calculations but focuses on maximizing instead of minimizing distances. Lastly, LeetCode 1769, which involves calculating the minimum number of operations to move all balls to each box, is another problem where cumulative distances within a structure are key. Exploring these related problems can help reinforce the concepts and strategies we've discussed. There are several approaches you can take to solve this problem, each with its own trade-offs. The brute force approach involves iterating through the string for each character to find the nearest occurrence of the target character. While simple to implement, it's highly inefficient, with a time complexity of O(n) squared. A better option is the two-pass approach, where you traverse the string left to right in one pass and then right to left in another. This ensures that you capture the nearest target character seen so far in both directions, achieving O(n) time complexity with O(1) space. It's efficient and relatively straightforward to implement. For those looking to optimize further, there's the one-pass approach, which combines the left-to-right and right-to-left logic into a single traversal using two pointers. While this method also has O(n) time complexity in O(1) space, it's slightly more complex to implement but reduces redundant passes over the string, making it an elegant solution for those comfortable with more advanced logic. Great job! In this video, we tackled the shortest distance to a character problem and explored an efficient two-pass solution. Remember, practice makes perfect, and each problem helps you become a better problem solver. Thanks for watching, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!